What if I told you the best way to build some of the strongest, most perfect solid materials was to actually start with a liquid? Yeah, it sounds a little bit crazy, but today we're going to dive into a chemical technique that does exactly that.
So think about this for a second. Imagine trying to build something thousands of times smaller than a single human hair. You can't just grab some tiny tweezers, right? The real problem here is control. How on earth do you put molecules together with absolute precision to create something totally flawless?
And the answer, believe it or not, is to start with a liquid. I know, it seems completely backwards, building a solid out of something that flows. But this is the real secret sauce for getting that nanoscale perfection. Instead of using tiny machines, we're letting chemistry do all the heavy lifting for us, building everything from the ground up.
And this whole amazing process has a name: the sol-gel process. And really, the name tells you the whole story. It's a journey from one state to another, from a sol to a gel. And this isn't just some neat lab trick either. This technique is fundamental. It's used to make everything from advanced coatings to medical implants, all by building things up molecule by molecule.
Okay, so to really get this, we've got to break down that name. Let's start with the first half, sol. What in the world is a sol?
Well, the technical term is a colloidal solution, but don't let the jargon fool you. All it means is that you have these teeny tiny solid particles, nanoparticles, just floating around suspended in a liquid. The key thing here is that they aren't dissolved, like salt in water. They're still distinct, solid little things just hanging out.
A really good way to picture this is to think about those little dust motes you see dancing in a sunbeam. It's basically like that, but in water. All these separate, independent particles just floating around, doing their own thing. That, right there, is our starting point. That's the sol.
All right, so we've got the sol down. Now for the second half of our clue, the gel. What is it, and what turns our soupy liquid mix into this new thing?
Now, a gel is seriously cool. It acts like a solid, right? But what's wild is that it's mostly liquid. The magic is all in its structure. It's this continuous, interconnected web of solid particles that forms all throughout the liquid, and it basically traps it.
You want to visualize it? Imagine a jar full of water, and then, poof, a massive three-dimensional spiderweb instantly forms inside, filling up the whole space. The web itself is the solid network, and all the water is now captured inside all its little pockets. That's our gel.
So the whole transformation is pretty clear now. We start with the sol, which is basically a liquid with all these free-floating particles, and we end with the gel, where those same particles have linked up to build a solid network, trapping the liquid inside. So, the big question is, how do we make that jump?
This, right here, is the heart of the whole process. This is the main event. It's that magic moment of transformation where all those separate little particles suddenly decide to link up and become a solid structure. This is the liquid-to-solid leap.
Okay, let's walk through it step by step. We start with our sol, right? Particles are just floating around. Then, we kick things off with some kind of chemical trigger. Suddenly, the particles start connecting, almost like a chain reaction, forming these little clusters. Then those clusters start linking up with other clusters, and it spreads like wildfire until a single massive network fills the entire container. At that point, the liquid is officially trapped, and we've got a gel.
So why go through all this trouble? I mean, what's the big deal? Well, the reward, the payoff, is in the absolutely incredible quality of the materials you can create. This is what we call the promise of perfection.
This quote really just nails it. It spells out the three huge wins you get: high purity, uniform particle size, and excellent control. For any material scientist, getting all three of those things at once is basically the holy grail, and the sol-gel process is what makes it possible.
So, high purity. Where does that come from? Well, it's because we're starting with really simple, pure liquids. We're building the material from the molecule up. This lets us dodge all the contaminants and junk that can sneak in with traditional high-temperature methods. The result is just an exceptionally clean material. Next up is uniformity. Because all the particles are forming under the exact same gentle, low-temperature conditions inside that liquid, they all grow to be incredibly consistent in their size and shape. This isn't random at all. It's highly ordered. And that's absolutely critical for getting predictable performance in things like catalysts or advanced coatings. And finally, maybe the biggest advantage of all, total control. By just tweaking the starting recipe, the chemicals, the conditions, scientists can pretty much dictate the final properties of the material. They can tailor its density, how porous it is, its exact chemical makeup.
They're not just making a material, they're designing it.
So, let's just put it all together. The sol-gel process is this really elegant, low-energy way to turn a liquid into a solid. But its real power, its real magic, is in the result. We can create these incredibly pure, perfectly uniform nanomaterials, and that gives scientists a level of design control that, honestly, used to be just a dream. And that really brings us to the most exciting part, doesn't it? When you can build materials with this kind of bottom-up precision, everything from scratch-resistant coatings on your glasses to new ways of delivering medicine in the body, it just opens up a whole world of possibilities. It really makes you wonder, with this level of control, what incredible new things are we going to build next?